So this type of calorimetry, we're going to really examine the change or the flow of energy from one substance to another. Okay, remember, hot flows to cold. Okay, so we're going to see the heat leave one item and another item absorb that. So this says you have a styrofoam cup with 50 grams of water that's at 10 degrees Celsius. So that's your cold thing. Your hot thing is a 50-gram iron ball that's at 90 degrees Celsius. It tells me the specific heat, right? S of H2O. And then it also tells me the specific heat of iron, right? It gives me both of those values. When we look at the heat transfer, right? The law of conservation of energy says heat is not created or destroyed, right? Energy is not created or destroyed. So whatever heat flows out of the iron has to be absorbed by the water. And so what we're saying here is the heat that is lost by one item has to be gained by the other. Does that make sense? We're just setting up the heat transfer as an equation, right? Whatever heat, if it's 100 joules of heat flows out of the iron, 100 joules of heat is going to flow into the water. Okay, so we set up that equation. We put a minus with the side that is getting colder to be able to counteract the fact that the temperature is going to be negative there, right? The change in temperature is going to be negative. Okay, if I'm getting colder, my final minus initial temperature would be negative. And so we add a negative here to the side that is getting colder, right? The side that is losing energy. So I'm gonna go ahead and take our equation and expand it out a little bit, okay? Instead of just Q equals Q, it would be MS delta T equals negative MS delta T, right? That's really what we're gonna use for our calorimetry equation. So if you want to put that one on your equation sheet, you're welcome to do that as well. This could be the side that is gaining energy, and this could be the side that is losing energy. Oops. Okay, if you want to make that little note there. But the negative is pretty important because otherwise you're going to have one side of the energy system that's negative and one side that's positive, and then they can't be equal, right? All right, so let's go ahead and look at this problem. It says calculate the final temperature of the water. But I want you to really think about this. If it's the final temperature of the water, isn't it also the final temperature of the iron? Right? It's going to come to an equilibrium. So when it says the final temperature of the water, realistically, we're finding the final temperature of both items. We're assuming here that it's coming to equilibrium. So let's set up our equation here. I'm going to call this side over here is the side that's gaining energy. So for me, this would be my water side, and this side would be my iron side. Okay? And then I'll just start plugging in the numbers that I have. So water has a mass of 50 grams. It has a specific heat of 4.18. And then we've got temperature final, which we don't know, minus temperature initial. Okay, that's all going to equal what's happening with iron. So I'm going to put in the negative because I know iron is going to start getting colder, right? The mass of iron is 50. The specific heat is 0.45. Temperature final, I don't know, but my initial temperature is 90. Okay, any questions about how those numbers got plugged in or why they got assigned to what variable? Do you see an issue here algebraically? We've got a variable on both sides, but isn't it the same variable? So we can distribute things out and then just combine our like terms, right? So we'll be able to work through the algebra there pretty simply. The one thing that I did want to point out, and we talked about this earlier, was that look at the difference in specific heat capacities between water and iron, right? So iron is going to heat up really quickly. It takes very little energy for iron to heat up, right? To get 1 gram of iron a degree hotter, it only takes 0.45 joules of energy. So it's going to heat up really quickly. So tell me, before we even do the math here, what's the expected range of our final temperature? That's right, between 10 and 90. There's no way we can get a temperature less than 10 or greater than 90, right? There's not possible. We couldn't come to an equilibrium outside of that range. If you had to take a guess, I want you to think one step further. If you had to take a guess, do you think the temperature is going to be closer to water or closer to iron? closer to water. I think closer to water because iron adapts to its temperature really quickly, right? Iron adapts to its temperature really quickly. And so water is going to take more coercing, right, for it to heat up. But iron will adjust really quickly. So let's do the math and see what we get, okay? There's lots of ways you can go about the algebra, so I'm going to let you do your thing with the algebra. And, yeah, we'll see what we get. That's what I got, 22.06. Is that close or no? Oh, shoot. All right, let's check mine again. Does that line of red match what your numbers have or no? Okay, so maybe I just did math wrong. 4115 divided by... Oh, I that's right. I subtracted that over. Okay. Divided by 209 plus 22.5. There we go. 17.7. There we go. Thank you. Okay, so does that fit our expectation? Does it at least fit within the range we said? Mm-hmm. Yeah, it had to be between 10 and 90. And did it match our guess of closer to water? Right? In this case, significantly closer to water. So I want you to step back and think, what scenario would cause the equilibrium to be greater or closer to iron? Give me some situations that could cause the equilibrium to be closer to iron's temperature than water's temperature. The water could start out hotter. Yep. Okay. That's right. The mass of iron would be significantly greater, right? The mass of iron would need to be about, based on the specific heat differences, the mass of the iron would have to be about 10 times greater, right? To get that equilibrium closer to that direction. But yeah, okay. Interesting. That's that equation for calorimetry. All right, and we're going to use that one quite often. All right, a cup contains 100 grams of water is mixed with a cup of water that's 10 degrees. What is the final temperature? Okay, so here we're just taking hot water, cold water, mixing. Do you have any predictions here? It's got to go between 10 and 90 again. Okay, you went specific with your prediction. I was just thinking hotter or colder, but okay. All right, let's see what we get. In this case, we're using specific heat capacity of water for both sides. Okay, so that can help with your algebra a little bit, right? This would be the hot side. This would be the cold side. So I'm going to go 500 times 4.18 TF minus 10 equals negative 500, 4.18 TF minus 90. So don't you have specific 4.18 on both sides?
Wait, what do we do? How do we get the same grams?
Oh, no, you didn't. I just wrote it wrong. This one should be a 1, right? Thank you. Off my game today. Okay, 100 grams, 90. It's the one that's getting, so it gets the negative. I will tell you, dropping that negative, forgetting to add in that negative is a common mistake. So just be really diligent about thinking through that negative. But we can get rid of the 4.18 since it's on both sides.